Okay, I think we can start from now. We have like 12 people in the room. Maybe this is how many competitors you want, if you apply for NIH grants. So today, my name is Shumin Wang. I'm from the National Institute of Biomedical Imaging and Bioengineering, also called NIBIB. It's one of the 27 institute or centers we call ICs at NIH. I'm going to present the Brain Initiative funding opportunities. Before I start, I'd like to give myself a quick introduction. I'm a program director at NIBIB. I manage two portfolios. The first portfolio is about electromagnetics. It's about MEG, EEG, or any diagnostic or therapeutic device that utilize electromagnetism. The second portfolio is magnetic resonance imaging. So all my portfolio is about magnetic and also big instrumentation development. I'm also the program director for the Brain Initiative. Actually, I'm a co-lead of one of the 6 teams in Brain called Team C, non-invasive brain imaging and modulation. So at the Brain Initiative, we develop the so-called funding opportunity announcement, and we solicit application like I'm doing here. And when your application got submitted and peer review got a score, then we have internal evaluation and recommend for funding. So that's my daily duty. So we have an hour, 15 minutes. I'm trying to cover my session with this at 57 minutes, but I think we have some kind of flexibility. So after my talk, if you have any question, welcome to ask. So we don't have too many people in the room. This gives you opportunity to ask more questions in a sense. Here's a review of my talk today. First, I'm going to introduce the Brain Initiative. The Brain Initiative, I think you can view it as a virtual institute at NIH. It does not have a physical building. It does not have its own program director. However, it has its own mission. It has its own budget, which is $400 million in 2019. What does $400 million mean? It's the same size as NIBIB, the institute I'm working at, huge amount of money. And also, it has many program directors from 11 different institutes. So altogether, we work to fulfill the goal of Brain Initiative. So you can view it as a virtual institute at NIH. So on this topic, I'm going to cover the mission of Brain Initiative, the strategy, and also the organization, how we develop a funding announcement, and how we run this program. The next topic is active brain funding opportunities and team activities. The Brain Initiative has 6 different teams. Each one publishes its own funding opportunity announcement. So on this topic, I'm going to go through very quickly the active funding opportunities that may be relevant to your background. So my understanding, you're all brain mappers, okay? Perhaps circuit level brain mapping. So some of the funding opportunities may be very interesting. And finally, application guidelines. So most of the Brain Initiative funding opportunities are actually so-called request for application, or RFA. It's quite different from those you are familiar with, called a parent announcement. There are differences. So on this topic, I'm going to go through very quickly what differences are to guide you pay special attention to something that could lead to better quality applications. I hope after this talk, you'll have a good understanding what the Brain Initiative is, what kind of funding opportunity is relevant to your research interest, and how to develop a better grant application. So that's my overarching goal here today. So why Brain Initiative? If you look at this chart, which shows the leading category of U.S. disability adjusted life years in 2010. Basically, it's an indicator of how severe each disease affects our quality of life. So as you can notice, neuropsychiatric disorder, which is a combination of mental and behavioral disorders, and also neurological disorders. First category, basically NIMH covers it. And second category is like Alzheimer's disease, Parkinson's disease. That's NINDS topics. All together, they account for 19% of all disability in U.S., which is the #1 cause of disability. So we all know that cardiovascular disease is #1 cause of death in U.S. However, the disorder related to our brain is the number one cause of our quality of life. So there's a huge need to further advance the human neuroscience to come up with better treatment of neuropsychiatric disorders. So there's a significant need here. So needless to say, you are all human brain researchers, so you like this message. So in 2013, NIH Director Francis Collins announced the Brain Initiative. The overarching goal or the mission of Brain Initiative is to accelerate the development, application of innovative technologies to construct a dynamic picture of a brain function that integrates neuronal and circuit activity over time and space. Okay, this is a very short statement. However, there are some important messages here. First of all, the goal of Brain Initiative is to construct a dynamic picture of brain function. So it's a neuroscience study, more about understanding the function of a healthy subject. We often use disease as a window to understand the healthy brain, but the overarching goal is not to study a specific disease like Alzheimer's or Parkinson's disease. So it's more on the neuroscience side in general. And secondly, important here is what kind of brain function are we interested in? It's actually multi-scale. Go down from neuronal level, like synaptic input-output subcell level, all the way up to circuit activity. It's a multi-scale information, and also span in both time and space. It's a comprehensive understanding of the human function at a multiple scale. That's what I'm very interested in. So now we have this goal. What strategy do we use? So in order to understand the brain, you can typically take two different strategies. Number one is so-called top-down. So you can come up with a hypothesis, then have a bunch of experiments to verify your hypothesis. Okay, so a lot of theories like this approach. Another approach is so-called bottom-up. You have a lot of observations or due to discoveries, and then from the observations, you deduce a theory out of it. So in order to have these new observations, you will need to come up with new tools to lead to these observations. So in history, it turns out that new directions in science are launched by new tools much more often than by new concepts. I didn't say that, someone else said that, but it's pretty much true. If you think about biology, without the invention of a microscope, we don't have an idea what bacteria means, okay? Perhaps we still, in our imagination, is some funny things that cause us sick, okay? So whenever you have developing new tools, developing new discovery, and new science. That's what happened, and also repeatedly in history in biomedical research. That's the strategy we are going to take. So the Brain Initiative will build on recent progress to create the tools. So we have a lot of investment in technology, create new tools that will accelerate discovery and build the foundation we need to reduce the burden of brain disorders. So this gives you a picture. We are not going to explore a hypothesis-driven top-down. We are going to from a bottom-up approach. Okay, that's why in the first phase of Brain Initiative, you will see a lot of technology development, and also is has been a focus of team, non-invasive brain imaging. Okay, so if you look at the Brain Initiative, it's a little bit like a NIH grant. I mean, write a grant, you need to have an overarching goal, you have a strategy, and what else? You have a specific aims. So think about the Brain Initiative as a gigantic neuroscience research. Overarching goal is to understand a comprehensive understanding of brain at multiple levels. So what's lacking here is specific aims. Okay, these are so-called high priority research areas for the Brain Initiative. So in 2013, NIH formed a team called the working group. Okay, and the working group basically consists of top scientists in each sub-area in neuroscience. They survey the field or the subfield of their research, and then they measure distance, so to speak, measure distance from the current status to the overarching goal, and come up with some area that the Brain Initiative need to invest in the next 10 years in order to achieve the overarching goal. So those are the 7 priority areas here. So you can imagine this as 7 specific aims in your gigantic NIH grant application. So what areas do we need to invest in the Brain Initiative, okay, to achieve our goals? Here are 7. The first one is brain cell type or cell synthesis. Basically, the goal is to build a part list of brain. If you think of the brain as a complex computer, you need to come up with, okay, maybe there's a transistor, capacitor, and inductor, all the basic parts. They connect together to form this a very complex circuit. So what are the basic components? That's the first high priority brain cell types. The second high priority area is tools for circuit diagram. Here the keyword is diagram. So this area is focused on the wiring diagram of those individual cells. You think about brain circuit, how do you wire capacitor inductors to form basic functional unit. Okay, so this is the focus of the second priority area. This area, it explores different skills, all the way from subcellular scale, synaptic input-output, which may require X-ray topography and ex vivo tissues for the study, and also cellular level, cell-to-cell connection, how to deform a basic functioning unit, and those things require cellular tools. Okay, and all the way up to circuit level. So how the basic function unit form a complex circuit that will involve non-invasive tool. So it's a really multi-skill. It's not so fixed at one skill. The third priority area is technology to monitor neural activity. So the keyword for this area is activity. So it has to be in vivo signals. If you think about the second priority area, it's more like a static, picture or structural information, how these individual parts are connected to a circuit at different level. It's more about static. Okay, so that may require some kind of structural imaging. For example, diffusion tensor imaging. You have structural information. Okay. However, on the third priority area, you focus more on the in vivo signal. So that means anything any information that can only be acquired by using ex vivo tissue is not included in this priority area. And one example is subcellular connectivity. If you want to use scanning electron microscopy to do ex vivo tissue study, it's not part of neural activity. Okay, so as you can see, it goes higher and higher and more to the real human application. The fourth area is precise interventional tools. Here the keyword is interventional. So what that means, if you think the second and the third priority area basically is a passive monitoring, monitoring activities, you don't probe. Okay, and then the fourth priority area basically is perturbation and detection technique. You perturb, you use TMS or DBS to perturb that function, and then you see what the reaction. So it's more on the interventional side. Okay, so this can cover different technology, invasive, a DBS electrode, or non-invasive transcranial magnetic stimulation. The fifth priority area is the theory and data analysis. You have so many tools, so many observations. Deduce a theory, explain what's going on. Okay, so if you are a pure neural scientist on the theory side, this could be of your interest. The sixth area is called advanced human neuroscience. Here the keyword is human neuroscience, human. Okay, so this focus on technologies that can either be only applied to human beings, okay, or can be translated to human. Okay, so for example, if you focus on rodent study, like require craniotomy, okay, have a bunch of electrodes in the brain to detect signal. There's no hope to translate to the human. That's pure science study. No hope to translate to human application. It's not included in the sixth priority area. Okay, so everything has to be related to human or can be translated to human in the future. So if you relate this one, if you relate this priority area to the previous one, to the third one, basically get rid of all these cellular level circuit analysis. You cannot build a high density probe for human at least within 10 or 15 years and apply to a healthy human subject. And the final area is the integrated approach. If you think about this picture, okay, it's beautiful. You've got 6 different areas. On the other hand, you can think, okay, sorry, you actually created 6 silos. Okay, you let people stay inside the silos without talking to each other. And the goal of the integrated approach is to break the silos so you can talk to each other, build a multi-skill or multi-model tools, and together have some new science. So that's the spirit of an integrated approach. So the working group published a report called the Brain 2025, which you can find a copy on the Brain Initiative website. You can find a lot of individual goals for each high priority area. They said, okay, in order to achieve something, you need to do what, okay, in each area. So how does Brain Initiative manage, okay, the grants to achieve those goals in those areas? The Brain Initiative, we have 6 different teams. These 6 different teams organized by science and also by activity. For example, the team D is called training and dissemination. It's a science agnostic in a sense. You need the training anyway. Okay, so they publish a fellowship or the career development funding announcement or SBR type of funding announcement, just more related to activity rather than science. The other 5 teams, like team A, B, C, E, and M, they are more on the science side. For example, team A is brain cell circuits and cell synthesis. It touches different cell types, like building a party of neural cells, and also how these cells wire together. Okay, so it touches this one. Team B is on invasive tools for neural recording and neuromodulation. So it touches this second, third, and different areas. So this is sort of a complex matrix of how different Brain Initiative teams manage this project to achieve the overarching goal in these 7 different areas. So the team I'm co-lead with Dr. David McMullen at NIH is so-called non-invasive neuroimaging and neuromodulation. So basically, we cover the goals in the tools for circuit diagram. We are more on the circuit level, okay, not the cellular level, more on the circuit level. And the tools to monitor neural activity. So resting state functional MR is one example. There are other examples. The precise interventional tools, that's you have transcranial magnetic stimulation or transcranial direct current stimulation, all those type of non-invasive transcranial stimulation tools. And finally, advanced human neuroscience, because all these non-invasive tools. So whenever you want to apply something to human, it could be non-invasive is number 1 choice. Definitely can have invasive DBS. Okay, that's covered by Team B, this invasive tool development. So we have these 6 different teams. Each team has 2 co-leads and consists anywhere between 10 to 30 program directors from across the NIH. So we publish something called a funding opportunity announcement, okay, which I'm going to describe a little bit in more detail next. So solicit funding applications, and when the application got reviewed, we have a team discussion and recommend funding to NIH leadership. So also there's a team called the coordinating team at the Brain Initiative that coordinate the activity of different teams. So that's how the Brain Initiative organized and function. Okay, so this is a snapshot of active funding opportunities in the Brain. It's not exclusive. There are more than this. Okay, so give you an idea what kind of funding mechanism we are using. As you can say, something you are very familiar, for example, R1 mechanism and R21, high risk, high impact mechanism. Something you are not quite familiar, for example, there's a U1 mechanism, and there's a U19 mechanism, and there's even something even strange called UG3, UH3. Okay, so you may have a question, how do you come up with so many different funding mechanisms? Why just use R1 straightforwardly? So the answer is depend on this. Remember, we are trying to develop funding announcement to achieve goals in the priority area. Depend on the scope of this funding announcement, the effort of each project. Okay, we decide what kind of funding opportunities is appropriate for that effort. Okay, if something is we think that need out of the box thinking, in the groundbreaking ideas to significantly move forward the field, then we will start with R21 type of thing. It's a high risk, high impact. Okay, if something we think there are a lot of ideas has been proved in this field, but we need to invest heavily to make sure they actually implemented and can be applied in others' lab, then we'll be more likely use so-called U1 mechanism. So the U, everything comes with U is something called a cooperative agreement. That's agreement between awarding institution and NIH program official. So you sign something and that one goes into your notice award. So by doing that, NIH program can have a closer oversight of the progress of your project. For what purpose? Okay, it can be ensure deliverable. Okay, for example, some of the tool development announcement we have, we'd like to say instrumentation to be built in 5 years. Then we have this U mechanism try to help, okay, to make it happen. And another example is this one. This team BCP. This one is a multi-team, multi-project consortium. So it needs a lot of coordination among different teams that require heavy NIH program involvement. So in that scenario, we also use this U mechanism. Okay, so NIH, roughly speaking, have like 237 different funding mechanisms. We only use less than 10% of that. So in that perspective, it's not that complicated. But keep in mind, so whatever funding mechanism you are seeing is a craft according to the scope of the effort we foresee. Okay, if high risk, or is a multi-project coordination, or is a full development or dissemination. Okay, what that means? That means when you apply from the specific announcement, you need to pay attention what this funding announcement is about. It's not all R1. Okay, open-ended research. So this is a history of the Brain Initiative. It's announced in 2013. We got a first award out in 2014, and what's significant happened is actually at the end of 2016, the 21st Century Cure Act was signed into law. So if you look at the Brain Initiative budget, it actually consists of two parts. The first part is need to be approached by the Congress every year. So you hear a lot about the congressional fights and the shutdown. This is already to the first part. Okay, you need to approve it year by year. And second part is actually relevant to this 21st Century Cure Act because it is signed into law. It does not need the Congress involvement to argue each year. So it's more stable in a sense. Okay, so after this signing into law, we have stable funding from year 2019. Actually, it's this year. So this is a geographic distribution of all the grants we have funded up to year 2017. As you can see, it's relatively evenly distributed across the country. Of course, you have a huge concentration in the East Coast. That's where Harvard and MGH they are. But you still have a lot of grants in the Midwest and the mountain region. Okay, and what's interesting is we do fund international grants. If you look at this chart, we have 3 grants in Australia, 1 in New Zealand. Actually, I have 1 grant. They have a subcontract to New Zealand University. And also in Europe, looks like we have 1 or 2 grants right here in Rome. And we have 2 grants in China and a few in South Korea. So if you have some good idea, okay, on your science, and you think it's applicable to Brain Initiative, go ahead and apply that. We never discriminate where you are from, locations. As long as science justifies itself, we are going to promote the science. Okay, So again, if you have any question, you have any concern about the international application, sometimes I get an email, okay, I'm in Europe, can I apply? The answer is, if the funding announcement does not say no, then you can. So one example is SBR, small business foreign entity cannot apply. But other than that, most funding announcement, international applicants can apply. It's not just for the US, it's actually for the entire world, in a sense. Okay, so this is a breakdown of how we spent in past 5 years. We don't have data in fiscal year 19 because fiscal year 19 will end on September 30th. So in the past 5 years, you can see a steady, or not steady actually, exponential growth of funding of our initiative. Start from 50,000 in 2014 and balloon up to 400 million in 2018. So as I mentioned, 400 million, that means it's bigger than NIBIB, the budget. If you look at the breakdown, okay, we can say this blue color looks pretty big. It's about 40% of all the funds in 2018. It's actually human imaging and modulation. That includes both invasive, like electrode, DBS, and non-invasive, MR instrumentation development. So if for your research, if you are interested in human circuit, okay, and this is good news actually. But we do find other priority areas that you can see from this chart. So here you can see a detailed picture of the budget, okay, historical budget. From year 2014 all the way to 2018, increased by 350 million actually. Now year 2019, we are close to 400 to 450 million this year's budget. Okay, and in the future, we'll have we'll have a huge influx money from the 21st Century Cure Act in 2023. And in any year, you can say the funding, okay, will not be less than what we have in 2018. So a lot of times I heard question from the investigator. They say, okay, I know burn initiative has been so many years. How about the money? It is running out. So this chart can give you a better idea how much money we have left. And also you can see from these bars, it's actually two parts. The basic, the light blue color is base funding that require congressional appropriation each year. But the green color represents the 21st Century Cure Act. It's signed into law. As I mentioned, it's more stable. Does not require congressional appropriation each year. Okay, so and overall, the projected total for the lifetime of burn initiative is close to $5 billion research money. So far, we have spent the cost a little bit less than $1 billion in the last 6 years. Okay, so as I mentioned, you can think the burn initiative as a gigantic, is perhaps the biggest ever in the history of a neuroscience project. When you do the project, often you need to have a retrospective view. How is it going? How many goals have been achieved? Are there any missing opportunities? Are there any new goals to achieve? We do the same in burn initiative. In 2018, we formed the second working group. It's also a group consists of many top experts from the subfield in neuroscience. They survey the field and look at what we have founded and give evaluations. So they have 3 meetings or 4 meetings in the fall of 2018, and they present to NIH at the end of December in 2018, and also presented at the burn initiative PI meeting in April. They have this draft report published online and has been open for comments. Okay, I believe the comment period has closed. This scheduled to publish the final report in mid-June. Now we are talking about that. Okay, so perhaps you'll see the final report no later than this summer. So in the final report, they will list, okay, perhaps not too much about what we have achieved. It's about the future, or gaps, or opportunities, or goals we need to achieve, and you should read that carefully. Okay, remember our mission, our job is to fulfill the goals. Whatever in there is likely will resonate in non-funding opportunity announcement. We are not trying to get a brainstorming and come up with big idea to do whatever we are interested. That's not our job. That's not how we steward public money. Okay, so read that report and you will get a clear idea of what's interesting in the future. All right, so actually you can find the Working Group 2.0 draft report online. Here I'd like to give some emphasis I grabbed from this report relevant to non-invasive brain imaging, give you some idea what we are interested in and what's in the field. So you're going down from the list, the number one is multi-scale imaging. So multi-scale imaging you can understand from different perspectives. You can combine information acquired by different models. For example, combine two-photon microscopy imaging with functional MR. Then you have a two-in-one, okay, information. That's one type of multi-scale imaging. And you may also try to get microscopic level information through macroscopic imaging, for example, diffusion tensor imaging. Basically, the voxel size at millimeter level. However, you get the direction information is a macro scale. Okay, so I encourage you to think aloud. What does this multi-scale imaging means? It could have different meanings. So the second emphasis in the report is to develop tools to analyze naturalistic and trained behaviors. So what does naturalistic mean? If you think functional MR, which is a bread and butter, arguably it's a bread and butter of circuit study, you put subject in a big cylinder in lying position. Perhaps that lying position is only natural to one behavior, that's sleeping. If you want to do like interaction, when people talk to other people, or play, let's say music instrumentation, that's not natural. Okay, so example of more naturalistic behavior imaging maybe a scanner that allows to image subject when they have some real task, perform a real task. Okay, not in lying position. That reminds you the monkey imaging MR sitting position versus lying position. So some kind of that concept. Or you can come up with some new technologies that allow imaging moving subject. Of course, this is not possible for functional MR. However, for optical imaging and especially for EEG, okay, that's possible. So that's naturalistic mean. Okay. The third sample emphasize here is achieve whole brain high resolution functional magnetic resonance imaging. Needless to say, high spatial temporal resolution is a holy grail to do functional MR study. The last one on the list is develop more human brain imaging technology beyond the functional MR. So functional MR you can understand narrowly, say this is BOLD or CBV, CBF. So what's beyond that? We know that functional MR, number one, the spatial temporal resolution is pretty much limited, okay? Perhaps by more for task-based than resting state. And also the contrast of functional MR, I remember like 3% contrast, which isn't that good. They need a lot of study and group average. So can you come up with some other new technology that break the barrier of the current functional MR? So I encourage you to think in that way. So in the next two slides, I will give you a few examples of the grants we have funded in order to achieve these goals. Okay, give you a better understanding what we are interested. So the first example is Wang grant led by Dr. Bruce Rusin at MGH. It's called the Connectome 2.0. So we know diffusion tensor imaging, basically you get the direction information out of the white matter neurons, right? Can we get the information more than that? So in this project, Dr. Bruce Rusin formed a wonderful team, a fantastic team, to do gradient design, new gradient, and also RF coil, pulse sequence, pulse gradient oscillating group, pulse gradient spin echo, PGSE, and oscillating gradient spin echo, and phantom validation. Okay, to develop sequences or methodologies that can allow you to detect the neuron size, its density, and its also cross-sectional shapes. So these are all macroscopic level information. However, you get the image, the resolution at the macroscopic, right? It's a millimeter level or sub-millimeter level. That's the meaning of one of the approach to achieve multi-scale imaging. Okay, so the second example is a Euro-1 grant led by Dr. Mike Garwood from University of Minnesota. They propose develop these new tools, new toys. So it's a head-only 1.5 Tesla brain scanner, but allow subject in a sitting position. Also, they had an opening window in the front, so the subject can see outside. And you can see their hands are free, they can perform complex tasks. Okay, so compare this one with a conventional MR scanner, give you some idea of what naturalistic imaging methodology means. But this is not 100% naturalistic. You cannot let subject jumping or dancing, but it's a big step forward. By the way, all the information are provided here. You can find online if you know how to use NIH Reporter. Okay, it's all public information. The next example is a Euro-1 grant led by Dr. Tom Hu at General Electric company. They propose develop a lightweight, compact, low cryogen, head-only 7 Tesla MR scanner for high spatial resolution brain imaging. So perhaps a lot of you have experience on 7 Tesla. You know how wonderful it is for functional MR study, but you all know the problem is so expensive, right? So the number I heard, it costs like $10 million to build a shield room and buy a magnet. Okay, so a huge amount of investment. So how can we reduce cost so more researchers can have access to 7 Tesla MR scanner? This is the overarching goal of this grant. So Tom Fu, they propose develop a lightweight, which only weighs 7 tons, and also the size is same as a 3 Tesla scanner. Okay, compact, low cryogen requires less than 30 liters of helium. Had only 7 Tesla. So had only they have this asymmetric gradient parameter you are familiar with. They have published the result. They can achieve a through rate of 900 millitesla per meter per millisecond. Okay, so you have a high through rate, you shorter echo length, you can have a higher signal noise ratio, and less speed artifact. So this whole thing is actually geared toward both functional MR study, but not only for that. Actually, they propose to develop a high strength gradient. The gradient strength is 120, 130, depends on, okay. So as you know, you want to do a diffusion tensor imaging. The sweet region for the gradient strength is anywhere between 100 to 150. So once this machine is available, it's much cheaper. Okay, this could be like 40% cheaper than available machine. You can swap existing 3T scanner with this compact system. You can also do high resolution, high sensitivity functional MR and diffusion type of imaging. The last example is in the category of beyond functional MR. Okay, so this is a U1 project led by Dr. Larry Ward at MGH. They propose develop a magnetic particle imaging imager for functional brain imaging in humans. So I'm not sure how familiar you are with this magnetic particle imaging. Actually, there are several grants funded by NIBIB. They are all in the bioelectromagnetics portfolio. So basically, you inject a spinel, the super paramagnetic iron oxide nanoparticles, into the bloodstream, and then use a gradient RF coil to localize those spinels. Okay, it's conceptually it's similar to magnetic resonance imaging. However, you don't detect the magnetization from a proton. You detect from a spinel. So what the advantage? Of course, high sensitivity, right? It's a contrast agent, a direct image contrast agent. And also in the context of brain functional imaging, you do perfusion imaging. You measure the CBV, and as a result, you can get the CBV type of functional information out of this. So in the paper published by Dr. Larry Ward, they demonstrate that the sensitivity of this MPI-based CBV is 10 times more than MR-based. Okay, why? Because you have a contrast agent, and that's specific for the blood perfusion imaging. So if this is available, you can see it's really beyond the conventional functional MR. So that's the example grant we have funded so far. There are many others. Actually, we found perhaps 10 of them, large grants. This is some example. Okay, so far you have some understanding of what the brain initiative is, how we organize, and how we operate. We have 6 different teams, right? So in the next few slides, I'd like to quickly go through some of the active funding opportunities each team has that may be relevant to your research background. So I'd like to start from my own funding announcement. This one is a reissue of this NIBIB, okay, 1703. It's a proof of concept development early stage next generation human brain imaging. You can find the detailed information at this link. Okay, feel free to take a snapshot you want. And the receipt date is September 3rd of this year. It's about 2.5 months from now. It's pretty quick. So what this is basically a proof of concept study, instrumentation, or sequence methodology development grant. Okay, we encourage early stage development. You only need to prove the concept within 2 years. You do not have to develop the whole thing in 2 years. And the budget is $300,000 direct cost for each year, and the total period is 2 years. So this is more like a R21 type of thing, to be honest. However, R21 has limited budget, $275,000 for 2 years. We can it's not enough, okay, in our opinion. So we use R1 mechanism to house it, but in spirit, it's still R21. It's a proof of concept methodology development in 2 years. If you have any question, you can send me email. We can have a further discussion. The second announcement or active funding opportunity is a reissue of this one, the 1704. It's actually a sister announcement, the previous one. The previous one is for proof of concept development. This one is for full-scale development. Okay, if you have technology, methodology already been proved concept, ideally by peer-reviewed publication, right? So you can apply for this one to fully develop it in up to 5 years. There is no budget limit. Okay, doesn't mean you can ask whatever you feel comfortable with. So the budget should be justified by science. Okay, and it's our program director job to make sure justification is valid. But there's no limitation on the budget. Sometimes I got application from outside, and they only request less than $500,000 direct cost each year. And afterward, why you ask this little? They said, because I thought it's a conventional R1. No, this is not. Pay attention to some budget section. There's no limit there. Also, the receipt date is September the 3rd. It's about 2.5 months. So this one, you have to demonstrate the feasibility of this one, okay? If you say, I only have the concept, it's such beautiful thing, I need $1 million a year to do it. No, we cannot fund you for that. And also must be applicable to normal human subject, non-invasively. Remember, so we are in a team to do non-invasive imaging primarily. Okay, so next one is from Team A, the human brain cell census. Okay, so you actually have a whole cohort of 6 active funding announcement. Okay, altogether, what they are trying to do, they are trying to build a three-dimensional Google-like, this cell type of information. So sort of, you can start from here, this anatomical information. You click at one location, they will give you what kind of cell there, and their connection with other type of cell. This is the concept, okay? And also you may type in the specific cell type, and this will give you the location over there. So sort of this is three-dimensional cell sensor type of map. Okay, so if you are your imager, you may find someone participate this one. You can provide anatomical information, or if you are circuit type of neuroscientist, they also want to this circuit level information. So you can collaborate with other researcher to participate in all these 6 different funding opportunities. If you have interest, go contact Dr. Yong Yao and Andrea both at NIH. So I think you can participate in this for this specific areas. So next one is Team B, is invasive neural recording and modulation. They have perhaps 6 or 7 different active funding opportunities with the same goal to have next generation invasive devices. That could be DBS, okay, or could be high density new recorders, single cell recorders, okay, and all these cover different stage. For example, there's some early stage development, is R21, and this one is more on the clinical side, and also this small business, SBR phase 2. Okay, so they have a whole bunch of this announcement cover different stage of this invasive device development. Okay, they also have this very interesting funding announcement about physics of neural stimulation. So if you are interested in transcranial magnetic stimulation or transcranial ultrasound stimulation, you want to understand the mechanism of it, this is a funding announcement you should apply for. Okay, so it covers both invasive and non-invasive part. If you have more interest, contact Dr. Nick Langos at NINDS or Dr. Sarisa Cruz at NISHD. They are the co-leads of Team B. Next few come from Team D. That's the training and dissemination team. So the first one is postdoc fellowship, okay, or F32 announcement. So here's the qualification. You have to be less than a year experience at your postdoc position, or if you are within 12 months to get your PhD. So sort of like a 2-year window. Okay, if you think the time you get your PhD is a dividing point, 12 months before or 12 months after, that's the time window you can apply for. Also, you must be a U.S. citizen or permanent resident in order to be eligible. And applicants can only come from U.S. domestic institutions, no foreign applications. So what difference between this Brain Initiative F32 and other fellowship from NINDS or NIMH? Okay, so number one, you have to identify something relevant to the scientific goals of the Brain 2025 report. So grab the Brain 2025 report to see which goal is resonant with your research. Okay, then you can go ahead. If, for example, if your research more on the tumor cancer, okay, then perhaps it's not too much. However, it's on the circuit analysis, then that's good funding opportunity. And second major difference, my understanding, you have better chance applying Brain Initiative fellowship than regular NINDS. NINDS fellowship pretty good, but this one you can have better chance to get it. The next funding opportunity is this diversity K99 training opportunity. Okay, so perhaps you know this K99 I00, the so-called kangaroo grants. Okay, you have to be less than 5-year postdoc experience, and that require 12 to 24 months of training. That's by the time you get this award, you have to stay in your current position for at least a year. So roughly speaking, if you are in the second or third year of your postdoc, this is the right time to develop application. Okay. So what difference between this K99 with regular K99? There are a couple of difference. First of all, this is a diversity. So to be qualified, ideally should be either underrepresented the group, okay, Hispanic, Black, for example, or has some kind of disability, or you are a woman, okay, this qualify for this diversity. So if you are one of this, so you have a huge advantage. Okay. Another difference is you must be a U.S. citizen or permanent resident. You know that for regular K99 does not require permanent residency, does not require green card. However, this one does. There are differences. And again, you must identify a research topic that is relevant to the brain initiative goals. And also my understanding, if you all qualify, if your background all qualify, you have much better chance of getting funded by this diversity K99 than other K99 mechanisms. So the next opportunity from the Team D is called Research Resource Grants for Technology Integration and Dissemination, the U24. You can find all detail at this link. So this is something very, very interesting. It's very different from our one. So what does it apply to? Okay, let's see. You come up with a new technology, you publish that, you already validated that. Okay, that could be a new algorithm to analyze the brain circuit. Okay, once you publish that, researchers from other lab want to use your tool in their research. However, you cannot give your tool to them. Why? It's in my lab, there's no user interface, a lot of bugs created by your students. Okay, so it's not in a state to be used by other users. So if you happen to run into that situation, this is the right mechanism for you to further develop your tool to give a copy to other users. It's not a pure research like R1, open-ended research question. It's more on the development and also send a copy to other labs. Okay, so let's say you got funded and then you clean all the bugs, develop a nice user interface, and develop a menu to use it and training videos so people from other labs can use your tool in their research. That will achieve the goal of this funding mechanism. It's called U24. To be honest, U24 you can use for many different purposes, but in the brain initiative in Team D, this is specifically used for this development and dissemination activity. If you have any interest, go ahead and contact Stephanie Furtick at NIH. She is running this funding opportunity. So there are a lot of interesting funding opportunity at the brain initiative. Okay, so you really need to identify one that's suitable for your research. The last one, no, not the last one. The next one is from Team E, the theory and modeling team. They also have perhaps 5, 6, or 7 different RFAs, but more on the theory part. But this one is recommended by Dr. Grace Peng, my colleague at NIBRB, and she thinks this might be of interest to you. So is the funding announcement you can find here is NS19-201. So what they're looking for? They are looking for a model, a hypothesis-driven experimental design with direct intracranial access to brain recording and simulating. So basically, they are trying to come up with project. You have hypothesis. You have then you need a bunch of experiment to verify the hypothesis, right? So what kind of experiment they are looking for? This invasive DBS or ECOG type of recording, not non-invasive. So if you have a background, you have a neurosurgeon, you are a neurosurgeon, you have background in ECOG or DBS, this invasive device design or application, go ahead and find a theorist. Together you can come up to apply for this funding opportunity. That's where your opportunity is. Okay, again, go ahead, talk to Dr. Grace Peng if you are interested. The final opportunity is from Team N, that's neuroethics group. This called research on ethical implication of advancements in neurotechnology and brain science is R1. Why is this? Okay, Brain Initiative have huge investment, and every year we see new technology get developed. Okay, however, can you apply this new technology to human subject in an ethical way? That's the question, because these technologies are new. We are facing new challenges. Okay, and one example we can say here, you develop an invasive device for children. Okay, you are going to embed an electrode in their brain for the rest of their life. Is there an ethical issue? I believe so. Okay, so if you have some new technology, maybe a circuit analysis, you can tell the subject instantly you have Alzheimer's disease in 5 years or 10 years. Do you need to tell the subject instantly? Okay, these are all ethical issues. Think aloud. It's okay. Think aloud. Okay, really encourage your thinking. If you have this kind of new technology, you think there's an ethical implication. Okay, go to the law school, grab someone who is good at laws, and come together. You can have an application. $300,000 direct cost a year for 4 years. It's not a small amount of money. And the program director who running this one is Dr. J. Churchill at NIH. Give him a call or email him to say, I have this idea. I have this collaborator in law school. It is a good fit, okay, or not. All right, so that's opportunities, and now maybe you are motivated to apply something. You already have something in your mind. So how do you apply? Okay, so first of all, you have to understand there are differences between the most Brain Initiative funding opportunities and the conventional R1. So most of them actually running a so-called request for application type of thing, RFA. So you may notice the some funding announcement that said RFA dash whatever. Okay, so for the R1, you apply. You are familiar with this so-called parent announcement or PA. So what's the difference? Parent announcement is more about investigator-initiated research project. You have a good idea in neuroscience, you go ahead and put in the application and submit to NIH or NIH. Okay, so your idea. However, this RFA is more like program director-initiated funding opportunities. So program director, we look at this Brain Initiative report, okay, that priority area. We come up with, okay, this is the area we need to invest. We define the scope of it. We do not define the exact science of it. We define the scope of it. Then you investigator go ahead to apply. Okay, as long as your application is within this scope, it's fine. So it's more like a program director initiated funding opportunities. So that's the difference. Okay, so in order to successfully apply for RFA, you have to understand the requirement, what we are looking for in the RFA. Then you can have a handshaking with the program director. Okay, so how to identify a funding opportunity? You go to the Brain Initiative website, and the first tab is called funding. So put the most important thing first. And also there's 3 tabs here. There's one called exist or active funding opportunity. You click that one, and it'll show you all these active funding opportunities. You may narrow down the search by type of specific priority area. There are like 7 priority areas in my previous slide. You tap that, and that may give you a better understanding of this opportunity fit your background. Okay, so suppose you identify a funding opportunity. What's the next step? The next step is read it carefully. Okay. Normally, I recommend recommend the investigator read it twice. The first time, just to give a general look. The second time, use a pen to highlight. Okay, what's relevant to your background or research. So, what you need to pay special attention is the application deadline. Okay, because we run RFA, it typically has only 1 application date a year. If you apply for parent announcement, 3 application days. That doesn't apply to RFA typically. Okay, pay attention to the application deadline. The budget size, it could be different, very different. Normally, it's larger than regular R1. For example, the one we have now, the 1703, $300,000 direct cost a year, and the regular NIDS budget, I think, is $250,000 a year. So pay attention to the budget, and also projected period. Okay, it's not always 5 years, 4 years. Sometimes it's 2 years, sometimes 3 years. Pay special attention to those areas. And there are some other areas you need to pay attention, and I will go through very quickly. So once you read the RFA and you have some idea what the next step, I would suggest you to contact the point of contact. His or her name normally appear at the end of the RFA. There's a couple of names. There's science contact him or her. So for what purpose? You definitely don't want to spam him, right? So the three main purposes. The first one is responding to the RFA. So remember I said this RFA is more sort of program director initiated research. What the program does is basically we describe the scope or the boundary condition. Okay, what kind of research we are interested. For example, it has to be non-invasive, has to be applicable to human. Okay, we describe the boundary. So you need to make sure your research idea is within the boundaries. It's called responsiveness. If it is outside the boundary, it's not responsive, your application will be returned without further review. So that's very important. Also, application requirement. So what specifically the program want to say in your application, you need to put that in your application. And finally, the review criteria. So you think about the application process. The first step is a handshaking between you and the program director. Make sure you are within the boundary. And there is another handshaking is between you and the peer reviewers. You want to have a good handshake. Okay, a reviewer judge the quality of your application. So how do they judge? It's all in the review criteria. There are a lot of questions to answer. If you can answer all of them satisfactorily, then likely your application will be reviewed well. If you cannot, then you are rolling the dice. You can also be successful, actually. So if you feel comfortable, you develop an application, you go ahead, submit. What we'll do? Basically, we have a team. We'll do a responsiveness check. We'll see whether each application fits in the boundary of the announcement. For those non-responsive, basically we'll return without peer review. So the next step is go peer review. Okay, hope you got a good score. And then we move to the funding recommendation stage. So major difference between RFA and the parent announcement is there's no percentile and pay line associated with these RFAs. A lot of times I got phone call from reviewer. So what the percentile of my application? The answer is no. There's no pay line. Because the way NIH calculate the percentile is basically based on 3 study section statistics. So RFAs sometimes they run just once a year. Okay, there's no statistics to come up with this percentile. As a result, there's no pay line. So you only get the priority score, the PS score. Okay, so that's the only thing you get basically, and also summary statement for sure. So the team, Bernish team will have a group meeting, discuss each application, and then make a funding recommendation. Goes all the way to the director for their approval, and hopefully you can get it funded. So in the last few slides, I'd like to use the example, the RFA EB 1703, to show some areas that need to pay special attention when you apply to this RFA. So again, this is sort of a handshaking between you and the program director, how to get this handshaking. When we develop this RFA, we do not start from scratch. There are a lot of policy things we cannot change, right? So we all use something template. Template can change from time to time. It has to be current. But we do have the instruction to modify certain areas. That's emphasize, okay, the focus of RFA. So we emphasize in those areas. We want you, investigator, to pay attention to our emphasize. That's how we do handshaking. Okay, so those areas that normally we put a lot of effort, and you need to pay special attention to that. So the first one is the funding opportunity purpose. This is like an abstract synopsis of article. So give you a big picture of what we're looking for. Okay, for example, this one we're looking for non-invasive brain technology that can be applied to healthy human subject. So if your idea is sort of resonant, you don't have to be exactly resonant with this concept, go ahead. If that's not resonant, look for other funding opportunities. So that's the first thing to pay attention. Then the second part, we typically do a lot of work is the part 2, full test of announcement, section 1, funding opportunity description. So here we are allowed to further describe the funding opportunity, what we are looking for. Okay, so it's more detailed version than the synopsis or the abstract. And often here we give you some examples what responsive applications are, and more importantly, what non-responsive applications are. Okay, make sure to take a look at the non-responsive examples. Sometimes they are not exclusive. If you find your application is actually one of the non-responsive examples, then stop. Okay, or contact the program director to make sure your understanding is correct. So basically, here we describe the boundary conditions. This is the boundary investigator allowed to play inside. Make sure you are inside this boundary. So the next section is the research strategy. Okay, buried in this PHS 398 research plan. So here we put detailed instruction on what components we want to see in your application. Okay, for example, for this announcement, we have this current state of art statement. You need to state what the current state of technology. Without saying this, the chance of getting good score is lower. Okay, so if you read this U24 magazine, there are more detailed requirements than this. For example, dissemination plan, whatever. So read this section carefully, put all these components in your application. And the last one is this section called the score review criteria. Okay, this is the place you have a good handshaking with reviewers. A lot of questions are listed here. Again, if you can answer almost all these questions, a lot of these questions satisfactorily, then the quality of your application could be higher than otherwise. Okay, so for each, there are 5 categories: significance, investigators. The first part we are not allowed to change. It's all boilerplate. Okay, but there could be a few questions in the second paragraph which does not appear here at the end. So those questions is what we specifically ask reviewer to look at your application. Okay, so pay attention to those non-boilerplate questions. You got 2 RFAs, you compare them, you'll figure out what's the difference. Okay, so this is a section you need to pay special attention to. That's pretty much about it. We have 8 minutes for question, and I hope you have a good understanding of what a burn initiative is, what funding opportunity are there that are relevant to your research background, and the general idea of how to write a good grant application. And I wish you successful.